All right, so as we start talking about basically working our kinematics problems, let's set this up by focusing on the acceleration. So we're going to really think about what the instantaneous acceleration is trying to tell us about. So we said, for starters, just in terms of its definition, that the acceleration is trying to tell us about how an object's velocity is changing with respect to time. So there's three ways for an object to change its velocity. It can speed up, it can slow down, or it can change its direction. So even if you have an object that's constrained to move along a line, so it's just a one-dimensional problem, it still has all three of these options, right? The object can speed up, it can slow down, or it can turn around. Now, the first two of these basically tell us about how the magnitude of the velocity vector is changing. The third one obviously tells us how the direction of the velocity vector is changing. And in a one-dimensional problem, pretty much what that means is we're going to pay attention to the sign of the velocity vector. That's the only way in a one-dimensional problem that the velocity vector can change its direction is to go from positive direction to negative direction or vice versa. All right, so there are a couple of words that we want to be very, very careful with when we're talking about acceleration. So they're accelerate and decelerate. And the problem is that we use them sort of all the time in kind of casual everyday language, where accelerate means speeding up and decelerate means slowing down. And the sort of danger here is that basically we know that both of these words, both speeding up and slowing down, mean that an object is accelerating. There has to be acceleration for both those things to occur because you're clearly changing the object's velocity. So we don't want to sort of put ourselves in a situation where in using the word accelerate to mean speed up, that we end up sort of thinking that, oh, accelerate only occurs when an object is speeding up. An object accelerates when it does any of these three things. Decelerate also has this dangerous connotation that we also think of it as, oh, it's accelerating in the negative direction. It doesn't have anything to do with acceleration in the negative direction. It simply is just a bad way or a way that we will avoid to say slowing down. So what we're going to do, instead of using these words, accelerate and decelerate, we're actually going to use these words, speeding up and slowing down. So the funny thing is that students tend to want to use these two because they sound more scientific, they sound more technical. When in fact these two phrases of speeding up and slowing down are actually very technical definitions. And so let's talk about what those definitions are. All right, so basically what speeding up and slowing down are trying to tell you about is the relative direction between the velocity and acceleration vectors. So for an object that's speeding up, so let's take this car here. Here we have it at some initial instant where its velocity vector points to the right and has this particular magnitude. Well, at some later instant, what we notice is velocity vector still points to the right, but now the magnitude of the velocity vector is much larger. So the speed has increased because the velocity vector's magnitude is larger than it was before. Well, the only way this can occur is if the acceleration happened to point in the same direction that the velocity vector pointed. So the object was moving to the right, but it sped up because the acceleration also pointed to the right. So in terms of the technical definitions for speeding up, again, there's two things that speeding up is trying to tell us. One is that the magnitude of the velocity vector is increasing. You went from a lower speed to a higher speed. So the magnitude of the velocity vector at this instant, aka the speed, is less than what it is here. But the second thing that speeding up is trying to tell us is that the velocity and acceleration vectors point in the same direction. And again, that's important information to know. Slowing down. Well, so there's my car initially. There it is at the end. And so what you notice here is the magnitude of my velocity vector has decreased as my car is slowed down. The only way this happens is if the acceleration points in the opposite direction. So the velocity points to the right since the car is moving to the right, but the acceleration points to the left, which is why the car is slowing down. So slowing down, again, tells us two things. The first of which is that the magnitude of the velocity vector is decreasing. But the second thing is the velocity and acceleration vectors point in opposite directions. So again, notice I haven't said anything about what the positive direction is. What I know is that whether the positive points to the right or to the left, the acceleration and velocity vectors have to point in opposite directions. Well, there is a third option, and it's if we have an object that's traveling at a constant speed. And again, for one-dimensional motion, basically what that means is your object was traveling with an initial velocity. That initial velocity had some magnitude. The final velocity has exactly the same magnitude. All points in between had exactly the same magnitude. So what this means is that the acceleration is actually zero here. So constant speed in a straight line, and this is a very important detail in a straight line, tells us two things. One is that the magnitude of the velocity vector is not changing. That's true for anything that travels at a constant speed. But things can travel at a constant speed, say, in a circle. And in that case, you would need an acceleration because the velocity vector, though its magnitude wouldn't be changing, its direction would be. So a constant speed in a straight line says not only that the magnitude of the velocity vector is not changing, that's the constant speed part, but also that the acceleration is zero. So if the magnitude is not changing and the direction of the velocity vector is not changing, then you have zero acceleration. So it's a very important little second piece of information here that's sort of required by our one-dimensional problem. All right, so how are we going to use this? Well, basically what we're going to do is we're going to use thinking about speeding up and slowing down to determine the direction of the acceleration. So there's sort of two pieces we'll do. First is we'll say, well, in most problems, we'll have a sense of which way the object is moving. If I know which way the object is moving, then I'll know the direction of the velocity. And then if I know the direction of the velocity and can think about whether an object is speeding up or slowing down, well, if I know that it's speeding up, then I know the velocity and acceleration have to point in the same direction. If I know that it's slowing down, the velocity and acceleration have to point in opposite directions. So because for most problems that will work, we'll have a general sense about the velocity of the object initially, and then how it's moving in terms of speeding up or slowing down. We'll be able to use that information to determine the direction of the acceleration. And as we'll see going forward, knowing the direction of the acceleration can be very useful in simplifying our Newton's second law problems when we get to that piece of this.